Yeah. So hello everyone and welcome to our, this is I think the fifth day, right? The fifth day of Astrosprint Discovery. We have an old friend with us, Sushan, who's been with us since the last two workshops that we've had. So welcome Sushan, great to have you with us. And yeah, and so Sushan is going to talk to us about neutron stars, and I'll take it over from here. Yeah, Sushan. And Sushan, there was a small element which we wanted to add this time, which I'm requesting many speakers. If it's towards the end, you can give a brief 5 minutes of how you got into astronomy and what were the hurdles you had, and because that would be encouraging words for participants who are looking for careers in astronomy. So
sure.
That would be a slightly informal part at the end. Yeah,
absolutely. Thank you very much, Priya. Let me start by saying, sort of expressing my gratitude to Dr. Priya Hassan and Dr. Najam Hassan for organizing this and taking astronomy to young people, research in astronomy to young people during this very difficult time that we are facing for more than 1.5 years now. And for me, it's been a very exciting journey with so many young people doing such great work. So today what I will do is 3 groups of people have been working together since last year on through this project, and they would present their work tomorrow, all 3 groups. Today what I will basically do is lay down the introductory part for them to present their work tomorrow, and sort of give an overview of why we are doing this work. Well, let me state up front that all 3 projects are interconnected, and so I will basically give an overview of what we are doing and why we are doing this. So let me share my screen. Yeah. So what we will talk about are interconnections of various neutron star classes. But before I begin, I should show the workforce. These are the people who are working, and I have only been, once in a while telling them this means that and that means this and so on. But they have been excellent. So there are 4 people in each group. There were a couple more last year, but because of their academic constraints and other, they did not continue. But they worked along the way for quite some time. So there are all of these 12 people now continuing with 3 projects, and they would be talking about interconnections between various other classes of neutron stars, which I'll talk about today, to these specific classes. So connection of magnetars to other classes, and millisecond radio pulsar group would be actually talking about the subclasses of millisecond radio pulsars and their interconnections, and they have come up with some very exciting results they would share tomorrow. And the connection of rotating radio transients to other classes. So I understand that there are some new people, young people who have joined for the first time today. So I will give a very brief and fast introduction to neutron stars, and because I have talked about neutron stars quite a few times in this forum, And I would urge the new people to go and take a look at the old lectures, and they would get more details from there. So this is what I define a neutron star is. A neutron star is the last line of defense that matter throws in its hopeless struggle against gravity. Why do I say that? Because gravity is the only long-range force that sort of controls all the phenomenon when we talk about larger and larger masses. And when the mass is large enough that there is nothing that can oppose gravity, then we have a completely collapsed state of affairs, and that's what we call a black hole. But today we would not talk about black hole, but the most compressed state of matter. So if you try to compress the matter a little more, it will become a black hole. So just before that, what we have is a neutron star. So we would not talk much about the interior physics, how that happens, but this is the maximally squeezed state of matter, which gives us a neutron star. And you see that the concept of this extremely squeezed state of matter is pretty old. It's about 90 years now that we have this concept. So this timeline is important. I show it in all my neutron star lectures. So is that in February 1931, Landau completes a work on maximum mass of white dwarfs. And you will see that the maximum mass is given in terms of universal physical constants. So there is the Planck's constant, velocity of light in vacuum, and the Newtonian gravitational constant. And m is the mass of the proton. Now, and from this, he predicts the existence of giant atomic nuclei like stars. Please remember, at this point of time, we had no idea about the the internal structure of an atomic nuclei. The detailed structure of atomic nuclei was not known at this point of time. So this paper is submitted on 7th January 1932. 17th February 1932, Chadwick submits the neutron discovery paper to Nature. So when Landau does this work, neutron is not known, it's not discovered. And Chadwick's paper and Landau's paper came side by side almost. So that's the power of physics arguments, that you are actually predating the discovery of neutrons to sort of conjecture the existence of such a squeezed object. In 1933, just about a week later, Walter Buddy and Fritz Zwicky in American Physics Society meeting says that the supernova, they estimate the energy that is that comes out in a supernova explosion of a massive star, and they say that if this amount of energy comes out, then what would remain behind is a compact object, and that should be like a neutron star. Now, please note that at this point of time, that the exact energy available for a supernova that's being emitted out of a supernova was the estimate was slightly wrong, because we still did not know about the neutrinos, and neutrinos actually take away almost all the energy from a supernova explosion. So those numbers were not exactly accurate, but again, the power of great physics arguments. Now, we were talking about early 1930s, and now we come to 1967. So almost 35 years later. So the concept was there from basic physics arguments, but our instruments, our observational capabilities, when they become sort of good enough for us to detect a neutron star was almost 35 years later. In 1967, I'm sure every one of you know the story of detection of a neutron star. Jocelyn Bell with her PhD supervisor, Anthony Hewish, they were working on interplanetary scintillations. While doing that, they detect regular radio pulses from this object they called CP1919. And now, then they finally realized that this object is not coming from any terrestrial source, and this is keeping a sidereal time of and the period of this pulses. As you can see, these are the pulses. These are the pulses. So this was interpreted after a lot of sort of checking of various parameters and so on and so forth. This was the first detection of a radio pulsar. Neutron star sending out radio emission beam as periodic pulses. So they were called radio pulsars. And till today, we have a number of neutron star observational classes, which would be the mainstay of our talk today. Now we have about 3,500 neutron stars, which we have observed in all these various observational classes, some in optical, some optical emissions, some in X-rays, some in gamma rays. But till today, the maximal number of neutron stars are observed as radio pulsars. So understanding the radio pulsars gives us the handle on understanding what happens for inside a neutron star, what is the physics, what happens near a neutron star, and so on and so forth. Now, a quick recap of where neutron stars come from. We know that stars come in all kinds of masses. Our sun is a somewhat low mass object. So stars with main sequence mass, I hope most of you know what a main sequence is. Main sequence is the phase of a star when it is burning hydrogen to produce helium. That is the main phase. That's the longest phase of a star's life, and that is what is known as the main sequence. So the mass of when it starts the main sequence, so it's called zero age main sequence mass. So if that mass is between about 0.08 to 8 times the solar mass, then it goes to a giant phase and a planetary nebula phase, and then ends up as a white dwarf, the mass of which should be less than the Chandrasekhar mass. And now stars which have slightly higher mass, between 8 to 25 solar masses, they would go to a giant phase and then end up as a supernova. And these are the objects which will give rise to neutron stars after the supernova explosion. That's the compact object which will be left behind. And the mass of this object, please remember that the I'm sorry, the mass with which it started was between 8 and 25 solar masses. But after all these phases and in the supernova explosion, the mass is, most of the mass of this object is lost. What we are left behind is a small object, 2 to 3 solar masses, and that is the neutron star. And if the original mass is even larger than 25 solar masses, then of course the final object that will be left behind after supernova is a black hole, and the mass is probably larger than 3 solar mass. So what we are looking at is this middle path and the end states of this mid-range stars, and those are the neutron stars. Now this gives rise to, as you can see, it's a 2 to 3 solar mass star, and I have said that this is the extremely squeezed, the maximally squeezed state of matter. The mass, as you can see, is about 2 into 10 to the power 33 gram, 2 to 4. and the radius is about 10 to 15 kilometers. So that is an extremely compact structure. So the binding energy, as you can see, is about 10 power 53 arg. People who have not done this estimate, I would urge young people to go and do this estimate yourself. And if you remember in a previous slide, I showed that that is the amount of energy that the neutrinos take away. So that is actually the binding energy of the neutron star. Really. And of course, if you calculate the Schwarzschild radius of a neutron star, then it becomes about 3 kilometers, and the actual radius is about 10 kilometers. So it's only 3 times the Schwarzschild radius. So the general relativistic effects are also quite important in near the neutron stars. Once again, because of the compact star, the object can rotate very, very fast. So the spin period it can have, the minimum spin period it can have is about half a millisecond. So you can see that these objects can rotate very, very fast. For comparison, if our Earth, given its mass and the dimension, the minimum spin period that it can have is about 1.5 hours. So much, much larger. Okay. Now, what have we observed? This is a theoretical limit, half a millisecond. What have we observed? We have observed 1.4 millisecond already, only 3 times larger than the theoretical lower limit. Okay, so our observation capabilities are now almost at par with the theoretical estimates. Okay. It also, because of the compact structure, it can support a very, very strong magnetic field. And I urge you to go and do this calculation. What is the central pressure of such a compact object? And if you equate that to roughly the magnetic pressure, if a very strong magnetic field is there inside the neutron star, you will get to see that at the center, neutron stars can support a magnetic field which is as strong as 10 to the power 18 Gauss. Of course, on the surface, we would not see such a strong magnetic field, because by the time the field comes to the surface, it should be much smaller. And what have we observed? We have observed this, about 10 to the power 15 Gauss, larger than 10 to the power 15 Gauss on the surface of a neutron star. Now, these are the objects which are known as this extremely strong magnetic field. Neutron stars are known as magnetars that he was talking about earlier, and they have certain interesting properties and so on. So these are the extremely sort of peculiar properties, physical properties of a neutron star, which arise out of the fact that this is a maximally squeezed state of matter. Now, I said that it sends out radio signals in a periodic pulse, and that is understood by this radio pulsar model. Now, neutron stars can rotate very fast, and they have very strong magnetic field. So that creates a strong electric field in the region near the surface of the neutron star. This strong electric field can, I'm sorry, can accelerate charged particles. It can pull out charged particles from the surface of the neutron star, and then it can give rise to pair productions in the magnetospheric region. And these charged particles, while moving in the magnetic field, the strong magnetic field of the star, they give rise to energetic radiation. And this radiation is in the form of, I'm sorry, this radiation comes as synchrotron, mainly synchrotron radiation, Compton scattering, and the radio radiation mainly comes from the curvature radiation. What is curvature radiation? Charged particles in a strong magnetic field gyrates around the magnetic field, and because the magnetic field is curved, it forms follows the curvature of the magnetic field. So it accelerates and therefore radiates. Now, the range of the spin period of the neutron stars, the observed range, is from a millisecond to about 10 to the power 1.5 seconds, which means some tenths of seconds. Surface magnetic field varies from 10 power 8 to 10 power 15 Gauss. So there's a hugely large range of magnetic field. And the rotational energy comes, the radiation, the energy of radiation comes at the expense of the rotational energy of this object. And from assuming the magnetic field to be a purely dipole, so assuming a dipolar model of the magnetic field, what we have is the E dot, the rate of change of energy, rotational energy, is proportional to the square of the magnetic field. So now this formula, we know that because of this radiation, the neutron star is slowing down, and we can, as we can measure the rate of rotation, the rotational period, the spin period from the observation, we can also measure how this spin period is changing, that is the change of the rate of rotation, and from there we can estimate. So we can calculate this one. We know omega, we know omega dot, and from this relation we can make an estimate of the magnetic field, the dipolar component of the magnetic field. And please remember that this is the method by which magnetic field is estimated for most of the neutron stars. There are other methods which can be used for different kinds of neutron stars, but this is what gives us the basic idea about the magnetic fields of neutron stars. Now, we have a rotating object which has a dipolar magnetic field, but all neutron stars are not similar. The magnetic field structure, even though we are assuming it to be largely dipolar, but it has structures and so on and so forth. So the radio profile, that pulse profile that is coming in, the energy profile, have wide variation in shapes, and they also have different shapes at different energy, that is at different frequencies. So you see here, these pulse profiles are at different energy bands. For example, this is the radio band, and you see there are different pulsars with different shapes of the pulses. But for the same pulsar, the pulse profile changes from radio to optical to X-ray to gamma ray. Okay, so for example, the change here, or for Vela, it's quite dramatic. Okay, or for this object, or for this Geminga. For example, this is a pulsar, a very well-known pulsar called Geminga. You see that there is absolutely no radio counterpart of this pulsar, even though we see it in X-ray and gamma ray. So there could be complicated beaming effect, because of which sometimes we do not see a particular pulsar in a particular energy band. What is beaming? Here is this, the energy beam which is coming to us like a lighthouse beam, and unless our line of sight is in the line of that beam, we would not, if our line of sight misses that beam because of some orientation, then we would not see that object. And beams of a pulsar can have different shapes. They do have different shapes at different energies, and therefore it's possible that for some pulsars we see them in one energy band, but we do not see them in a different energy band. So this is a rough summary of the dipolar model and how it gives us a handle on the estimate of the dipolar magnetic field. And from here, we can also estimate a characteristic age. Assuming that a neutron star is born with a very, very fast period, effective zero spin period, and therefore looking at its p dot and p today, we assign a characteristic age to the neutron star, which is somewhat of a reasonable estimate for the actual age of the neutron star, but it may not be very accurate. In certain cases, it's rather off. It could be very off, but it gives us some handle on the characteristic age. Now we are talking about radio pulsars, and I said I would talk about various observational classes of radio pulsars, but I also said that of neutron stars, but I've also said that the radio pulsars comprise the largest class of this. I said about 3,500 neutron stars have been observed, and almost 3,000 of them are radio pulsars. So when we talk about neutron stars, these comprise the biggest class, and therefore one has to consider them a little more than the others. All right, and then there is another reason for doing so today, which would be clear in a little while. So now when we talk about radio pulsars, there are these periodic pulses, very regular periodic pulses coming to us, and there are certain timing phenomenon that happen. What do I mean by timing? That something happens in time. These are called you, instead of getting periodic pulses, you get some jitters, and there are very specific type of jitters that we see in radio pulsars. In particular, there are two main kinds of jitters. One is null, one is glitch. So let's talk about them. Null is very simple. What happens is, this is like a representation of a regular radio pulsar. We have very periodic pulses coming to us. So here is the energy, and this axis, the x-axis, is time. So with time, we are getting a series of periodic pulses. Now, for some of these radio pulsars, a very small fraction so far, about 200 of them, what we see is suddenly the pulses disappear for a little while, then they come back, and then they disappear again, and so on and so forth. This kind of pulsars are known as nulling pulsars. There is a period, there is a pulse null in between. There are no pulses for some amount of time. And there are cases of extreme nulling, when we only get a few pulses, and most of the time we don't get anything at all. And an even more extreme case of such a behavior are the RRADs. What is an RRAD? It's rotating radio transients. Why do we call them transients? We get, once in a while, we get a pulse from them. And as you can see from the nature, this is drawn in a particular way. You see that if you get pulses like this, you are not seeing a periodic pattern to begin with. Okay. Now, people have now established methodology to find the RRAD period by observing them for a very, very long time and trying to find what is the, so to speak, the GCF between the gaps between, let us say, between two pulses. So you get a pulse now, and you get a pulse now, and you get another pulse at some other time. So assuming that these pulses are actually there is this intrinsic spin period associated with it, so you can look at all the differences between pulses, and you can find the greatest common factor, and that will give you something like a spin period. So people have established these methods, and they find the spin period of R rats. And as you can see from this description of these nulling pulsars and extreme nulling, by the way, these pulsars which null very extremely, they are called intermittent pulsars. They are pulsars intermittently. So as you can see from here that it would be very natural for people to try to associate an intermittent pulsar with an R-rat. So people might think that, okay, we have intermittent pulsars, and probably R-rats are similar kind of objects, and they're just even more extreme than intermittent pulsars. So therefore, when you talk about nulling pulsars and when you look at R rats, it would be natural for people to connect these populations, and people have suggested such a connection for quite some time. It's almost 2 decades now when people suggested it for the first time that R rats are probably connected to nulling pulsars. For a while, there was not a proper way to see whether these two populations, these two types of objects are connected. And so what has happened is a couple of years ago, there was a few years ago, a student, Vishal Gajjar from NCRA, he's at Berkeley now. He created a list of all the nulling pulsars known. Till then, we did not know how many nulling pulsars are there and what was their behavior. And a couple of years ago, we compiled a comprehensive list of nulling pulsars. And one of the groups that you will listen to tomorrow have looked at, they have compared the nulling pulsars with R rats. And now they have something definite to say vis-a-vis the suggestion that was given that nulling pulsars are probably connected to R rats. So now you see, here is an example as to how we are trying to connect, trying to see whether there are possible connections between different observational classes. When I say different observational classes, I basically mean that their observational characteristics are different. So we're trying to see whether we have, connections between various neutron star classes. So this is just an example of how we see the nulling behavior. The nulling behaviors could be totally different. No two nulling pulsars are similar. You look at this object, these black portions are when there is a signal, and these blank portions are when there is no signal. So this has sort of regular nulls. For example, look at this one. This fellow is mostly nulling. The signal comes only for a small amount of time. For this object, the nulling episode happens at a large interval. This fellow has a signal at this point of time, and there is no signal for the duration of the observation. So there are all sorts of patterns that you see in nulling objects. And they are also associated with various other physical processes, as you can see in the pulse profile. So if the pulse profile, the average pulse profile looks like that, and then there are these sub-pulses, and these sub-pulse pattern shifts, and this shifting is associated with nulling behavior. It's not normally seen in pulsars that are not nulling. It also changes mode, that is, it switches frequency, the radio and X-ray brightness. Please remember that when you talk about radio pulsars, it's not that they emit only in radio. They also have, actually most of the energy comes out at higher energy band. So it has radio emission, and it also has high energy emission. For example, this particular pulsar has radio and X-ray emission both, and one sees that when it is nulling and when it is not nulling, the radio and X-ray brightness switches. So this is called mode changes mode, and we see that maybe I would come back to this plot later. The other kind of phenomenon, the timing phenomenon that we see, are called glitches. So there is a pulsar is slowing down smoothly. So you have a p dot, and suddenly there is a spin up of a neutron star. The spin up, the amount of spin up, if you see, may appear to be very small from terrestrial context, but these are actually very large. If you remember that we are talking about spin periods about a second or so, and the period derivative ranges from about 10 to the power minus 15 to 10 to the power minus 21. So p dot are very, very small values, and in that context, delta omega by omega ranges from maybe minus 6 to 10 power minus 9, and that's a very large number in this context. So there is a sudden spin up that happens, and this is a very complex physics that one has to explain. So this is another sort of demonstration of how this happens. So p is increasing, it's slowing down, so the spin period is increasing, and suddenly the spin period decreases, and then again it follows the original nature of slowing down. Now, in order to understand the glitch phenomenon, one looks at the magnitude of the glitches, and it's seen that it's very clearly bimodal. And we had a small paper a few years ago saying that showing that this is bimodal, and saying that there might be two different mechanisms associated with different magnitudes of glitches. So we see a phenomenon, and we are now saying that there are different processes happening in these neutron stars. Glitches, once again, are seen only in about 200 objects so far. Sorry, this is a repeat slide. Okay. Oh, I'm sorry. So now in all of neutron star physics, what is very important is the magnetic field. As I have already said, that surface magnetic field is about 10 power 8 to 10 power 15 Gauss, and so that's we assume it to be dipolar at large distances. So if it is a dipolar magnetic field, the interior magnetic field probably looks like this. It's a star-centered dipole. We are not sure what the interior magnetic field really looks like. This circle represents the surface of the neutron star. It may also look like this. This is again the surface of the neutron star. One understands that the interior of the neutron star could be superconducting, and there is complete flux expulsion. People who have studied that in your physics courses, superconductivity may expel magnetic flux completely. So such a phenomenon might happen inside a neutron star, and then the interior magnetic field may look like this. Outside, it would again follow a dipolar pattern or whatever. Now, people have also suggested, looking at various observation and the pulsar emission physics, that it is probably not purely dipolar, but has very strong multipolar component near the surface. And so these come from various observational signatures. So we really do not know what kind of magnetic field there is on the neutron star, and we mostly assume this to be a large-scale dipolar field. But from time to time, for various particular situations, it is seen that unless and until we assume the presence of strong multipolar components, we cannot explain the physics that's observed near the neutron star. So this is what a summary of the magnetic field structure of neutron stars. It's dipolar field at large distances. We estimate that the dipolar field from secular spin down, if the neutron star has a binary companion and there is an accretion process going on, material is being transferred from the companion onto the neutron star, then if there is channelized accretion, we assume that the magnetic field is strong enough to channel the plasma particles to the neutron star polar cap. Then the dipolar field at the Alphen radius is given by this. And in many accreting neutron stars, we sometimes it's possible to obtain cyclotron line emission. Then we get a direct measurement of the magnetic field, but of course we do not have any handle on the structure of the magnetic field for such cases. So there are uncertainties in the magnetic field, in our understanding of the magnetic field, and we do not understand the multipole structure near the surface. We do not understand the total field structure, and what I have not mentioned here is we really do not know what is the internal structure of the magnetic field inside the neutron star. And that is important to understand the field evolution and how one particular class of neutron star may evolve into another class of neutron stars, and about which we will learn now. I would skip that. Okay. So this is a diagram which I'm extremely fond of. It keeps changing. I mean, I have to update this diagram every now and then. As you can see, this is a plot from 2017. In 2021, the plot has changed slightly. I haven't been able to put in that new plot here. So you see these different colors and different legends basically tells you that there are different types of neutron stars, that they have different observational characteristics which are listed here. And I'm not asking you to read all this and understand, but just saying that just know that there are all these different types of neutron stars. And you also note that these orange colored objects, there are different legends. These orange colored objects are called RPP, radio pulsars. They are rotation powered pulsars. The energy is coming at the expense of the rotational energy. So these are all these 3000. In this plot, probably it's not 3000, whatever, maybe it's 2500 or something. So these objects are the radio pulsars that we have been talking about. These red objects are the magnetars. These cyan objects are rats. And I have not shown here, but the Nulling pulsars would be in this region where it's becoming sparse, and the glitching objects would be on this side. So what we try to do is one of the main activities that many people are involved in, the interconnection between neutron stars. And now this is becoming a very important line of investigation. There is an IAU workshop a few months down the line, which is bang on this topic on interconnections of different classes of neutron stars. But so this is just to say that this is a very exciting area of research at the current moment. So now, before we can talk about evolutionary links, we have to understand what these classes are. So primarily, they can be separated into three classes. Now, these three classes are classes of they are different method of energy generation. As I have said, the typical radio pulsars that we usually talk about are the rotation powered pulsars. They are seen in radios, they are seen in gamma rays, and also in X-rays these days. The energy of emission comes at the expense of rotation. Now, in this rotation powered pulsars, we see the classical radio pulsars, and then there are recycled radio pulsars. I'll say in a minute what these recycled radio pulsars are. They are mainly radio pulsars which are millisecond radio pulsars and mildly recycled, meaning their spin period and magnetic field is in between millisecond and classical radio pulsar. So let's go back to this picture. So here we have all the classical radio pulsars. The spin period is about 1 second thereabouts, and the magnetic field ranges from about 10 power 11 Gauss to about 10 power 13 Gauss. And now these objects are the millisecond radio pulsars. As you can see that the spin period is around millisecond and the magnetic field is very small, about 10 power 8 to 10. And these objects, these in-between objects, are known as the mildly recycled radio pulsars. What we understand is these objects are actually born here, and because of certain processes that happen to them, they are recycled into this area. Now, the second class of objects, and the rotating radio transients are part of this group, of course. Now we have the accretion powered objects. What is happening here? Neutron star has a binary companion, and material is being transferred from that companion onto the surface of the neutron star, and because of that, X-ray is being emitted. So the source of energy emission is the process of accretion. So these are called accretion powered objects, and what we have basically are objects which have higher magnetic fields, and these are actually sitting in HMXB, that is high mass X-ray binary. The companion is a massive star, and on the other hand, we also have low magnetic field objects. Magnetic field is smaller. They are sitting in low mass X-ray binaries. The binary companion mass is much smaller, and there are specific evolutionary processes because of which neutron star sitting in an HMXB retains a higher magnetic field, and a neutron star sitting in an LMXB has much smaller magnetic field. Those are details of magnetic field evolution. Then, for want of a better name, we call these objects as internal energy objects. So this is sort of a cluster of things that we have put together. I mean, it's a bunch of objects. We do not know much about them, and we have put them in this classifications where the source of energy is some internal process. For example, the magnetars, it is understood that the energy of a magnetar basically comes from the decay of the extremely strong magnetic field of these objects. The isolated neutron stars, you will see that what do we mean by isolated neutron stars? These classical radio pulsars, so most of them are isolated. So when I say isolated neutron star, I basically mean a set of neutron stars which are nearby and which are rather young, and they are still hot because they are young. They're born in supernova, so they start with a very high temperature, and because they're very hot, they are emitting an X-ray. Now, this X-ray is not channelized like the accretion powered objects like this, and it's not as strong. They are visible because they are nearby. So these isolated neutron stars are visible in X-ray because they are nearby. So they are separately called isolated neutron star. They also have different kinds of name, but isolated neutron star is a name that I personally prefer. There are other objects called compact central objects. So when a supernova explosion has happened, and we expect a neutron star to be there, and we have certain emission signatures from them, but they are not yet emitting as radio pulsars. So these are called compact central objects. And there are some suggestions that after a while they may behave like radio pulsars, and there are some conjectures that they would probably behave like magnetars after a while. So this is not very clear what these objects would do after some time has evolved. So these objects are basically objects sitting at the center of a supernova remnant. So now you can see that I have put in some arrows. So these arrows are basically, so if a rotation powered pulsar, a classical radio pulsar sits in a binary. So suppose I have a neutron star which is a member of a binary, then the accretion process would change its magnetic field and its spin period, and it would return classical radio pulsar to this spin. So if a classical radio pulsar has a companion and undergoes, a phase of accretion, then those radio pulsars would re-emerge or get recycled as millisecond radio pulsars or mildly recycled radio pulsars. So there is a channel of connectivity between them. There is also another channel of connectivity between these internal energy objects and the rotation powered pulsars. Now, this is the channel which people understand is because of the magnetothermal evolution of these objects. Please note that all of these objects are extremely young. Comparatively, these objects are older. So what one understands now is that magnetothermal evolution of these young objects might connect them up to the objects in this bin. So that is the area of excitement at the moment connecting these objects. So I will skip this. Or maybe just mention that. So this is a spin period histogram of all the radio pulsars, and this huge peak corresponds to the ordinary classical radio pulsar. See, the spin period is around 1 second or so. This is in log, and there is another peak near the millisecond spin period. And we understand that objects from here would be recycled to this bin if they are sitting in LMXBs, low mass X-ray binaries, and objects from here would go to this small peak here, which are mildly recycled pulsars if they're sitting in HMXBs, the high mass X-ray binaries. So here is a picture to explain all that I have been saying. So here is your regular radio pulsars. Now they keep slowing down. When they slow down, they cross a line which is called the radio pulsar death line. What is this death line? The process of emission. You remember it was the in the beginning of the lecture, I talked about how radio emission, how emission happens in a radio pulsar. There is a strong magnetic field and it's rotating. It creates an electric field. It pulls out charged particles and they move in the magnetic field, and there is emission from those particles, and that is how we see emission from a radio pulsar. Now, the combination of the magnetic field and the spin period would determine the strength of the electric field. If this combination goes below a certain value, the electric field is not strong enough to generate these charged particles, and therefore the process of radiation stops. And that is what is known as the death line. So when a pulsar crosses this line, the emission mechanism stops, and the neutron star exists, but there is no emission from there. Now you will say that, well, you have drawn this death line and I see quite a few objects there, orange objects there. Yes, of course. The calculation for radio pulsar death line has huge amount of uncertainty, because it's been more than 50 years now that the first neutron star, the first radio pulsar was observed. We still do not understand the emission mechanism very accurately. Okay, so therefore, if we do not understand the emission mechanism very accurately, of course, our understanding of the death line, our calculation of the death line is not very, very accurate. So what I have drawn here is a representative line, and the more sort of very accurately drawn lines, theoretical lines, also have the same problem. There would always be some objects which are beyond the death line. Anyway, so they're slowing down, and when they slow down and cross the death line, you're not supposed to see them. So what are these objects? These objects are actually the objects sitting in high mass X-ray binaries, because they're emitting in X-ray. That process is completely different, and that has nothing to do with the mechanism of emission in a typical radio pulsar. Their energy is coming through the accretion, and because of that, you see this extremely slow pulsars. So these are sitting inside high mass X-ray binaries, and then they get and they are not seen as radio, they are not radio pulsars. So now because of this accretion process, their magnetic field and their spin period changes, and they move to this region. So when accretion stops, they are seen as radio pulsars in this region. So these are the mildly recycled radio pulsars, and some of the objects which are sitting in low mass X-ray binaries, they would follow this path and they would emerge here. So this is why they are called recycled. When the accretion stops, you wouldn't have seen them otherwise, but because the process of accretion has changed their magnetic field and the spin period, they move to these regions, which is above the death line, and they are seen as radio pulsars again. So this is what is called a pulsar recycling. So what you are seeing here is an evolutionary connection between this set of objects and that set of objects. So if some of these objects have a binary companion, undergo accretion, they would come here later on. So we see this connection. Now, this connection at one point of time, understanding this was very, very important. And now we feel that we have kind of understood this. So there, there would always be some parameters and various issues that need to be ironed out, but the overall picture is more or less clear to us now. What we do not understand is this region. Okay, so this is the region which we wish to understand at this point of time. So here are the magnetars, here are the R-rats, and ignore the yellow ones. Those are extragalactic neutron stars, not a separate class. They're just seen in other galaxies. Here are the magnetars, and here are the R-rats, and we have the Nulling Pulses in this region. And as I have said, that people were trying to connect R-rats to the Nulling Pulses because they seem to be similar. On the other hand, you see in this plane, the R-rats are very close to the magnetars. So some people also try to connect these two populations. So what we have done, all the people from this project for this last 1 year, we are trying to look at the connection of the magnetars, the connection of the R-rats, and we are also trying to look at these objects, the millisecond radio pulsars. You note that we have these orange objects and we also have these black objects. Now see, the orange objects have a tag called GD, that is the galactic disk. And the black objects have a tag called GC, that is globular clusters. Now, a few years ago, we saw that the magnetic field and the spin period values of the millisecond pulsars, even though they would be coming from similar recycling processes in LMXBs, the average magnetic field, the average spin period values seem to be different between the galactic disk and the globular cluster objects. You will see that the globular cluster objects, for the same spin period, most of the globular cluster objects have a slightly higher magnetic field. And we had put out some theory about it, and people seem to accept that suggestion. So what happens is that even without the millisecond pulsar, even though we understand how the millisecond pulsars could be generated from this regular radio pulsars, it seems that difference in the evolutionary pathway can give rise to different final parameter values, and one group is looking at that, the classes, and there are also some other manifestations of it's not only the difference in the magnetic field, and there are some other parameter differences between these classes. So that's what the other group is looking at. So what we are doing is basically we are looking at so this part of the connection has been investigated for quite some time. Now what people are interested and what we are also looking at are these regions, the magnetars, the I'm sorry, the R-rats, the glitching pulsars would be in this region, and the nulling pulsars. So these are the connections we are trying to look at, and the people who are actually working on these would be talking about it tomorrow. So I would like to finish this here. These are all these databases that we have been using. I have not added here. I think some of them would talk about the database that I have created for the nulling pulsars. So that should also be here. We have not included it here. And so we will talk about the details of the work tomorrow. Thank you very much. I would finish here and take questions from here. You are muted, Priya. You are muted.
Sorry. So thanks, Sushan. Thanks so much. And I'm sure all these students, some of them are in touch with me. They're really enjoying working with you. And it's, getting us to the basic purpose of the thing of getting students to actually do research. So I'll start off with the questions. There's one from Iftisha. Ma'am, what's the difference between pulsars, quasars, and magnetars?
Okay. Quasars are a completely different beast. They are actually centers of galaxies, which I have not talked about at all, and which is not my area of expertise. And as I said, the pulsars and magnetars are different manifestations of neutron stars. Pulsars we have talked about in detail in this talk. Magnetars are basically neutron stars with very strong magnetic fields, about 10 to the power 14, 10 to the power 15 Gauss. And because of the strong magnetic field, they have certain different characteristic observational phenomena associated with them, but they are basically isolated neutron stars with very, very strong magnitude.
Yeah, the name. Sanket asks, does charged particles following the closed magnetic field lines also contribute in the main pulsar radiation beam?
No, not really. It's actually the charged particles moving in the open field lines. That is the radiation that comes out. The
Okay.
which level of studies are you in?
Yeah.
I'm in TYBSc, ma'am.
Huh? Okay.
Third year of this.
Okay, third year of BSc. So maybe it's slightly advanced for you. There is a beautiful set of lectures given by Professor Dipankar Bhattacharya of IUCA. He has given a set of lectures on the pulsar emission processes, which you can go to the internet and can search for it, and you will find it. And if you are interested in emission processes, you can listen to that. At least the first couple of lectures, it's very, very beneficial for understanding what is happening near the pulsar magnetosphere.
Yeah, ma'am, sure.
And Sanket has another question. What makes pulsar emission coherent?
Okay. So you you have to listen to those lectures, but it's basically coherent plasma processes in the magnetosphere. Coherent plasma processes. Yeah.
Any more questions? Please feel free to ask. Because tomorrow, ma'am will not be talking, the students will be talking. Yeah, okay, there's another question, I think. Yeah. Oh, Redan Ahmed is asking how to get started with basics of neutron stars theory as well as research regarding the same. Yeah, so Redan is a new student, so there would be some new students.
Okay, so I would suggest, actually this time I have not put up the basic references. If you go to the older lectures, I'm sure you know the previous lectures from this OAD project that Professor Hassan's YouTube channel has. So you can go there, and I have put up some basic references for neutron stars, and you can start with those.
Yeah. So go through there too. There's a playlist for astronomy for archival data. In that you'll find, I think those were 3 lectures, right?
Yeah.
And then there was another workshop after that, which was Astrosprint Enterprise. I think that has 2 lectures.
I think the first set has all the basic.
Yeah, so you can so just go to the YouTube channel and check different playlists. The playlists are ordered as per the workshops. So look for the astronomy for archival data one and check up over there. Julie is asking you, is there a new project this time?
Is there a new project this time? Actually, I mean, there are projects and projects, and we are trying to finish these 3 projects right now. If you are interested, let us see how things evolve.
Yeah. Like I mentioned to everybody, when we finish the workshop, you could express this thing of doing project with someone, and then we'll pass on to the list to ma'am or whoever you want to work with, and it can be planned accordingly.
Another thing we can do, Sushan, is the people who already worked with you, they can start mentoring the new ones.
Yeah.
Because so we could do that. So Julie, we can start off with the projects which would initiated last time and can be extended later, but we will see to it that the people who have progressed well already in the previous ones can start mentoring, rather than senior people again starting all over again.
So we'll at the end of the thing, I'll share a Google form where you can share what are the ones you want to go in for, and then we can, like sir is saying, I think a good idea would be to make the previous ones the mentors. Ma'am will anyway be there, but you already have a set of
very, very good idea.
Yeah,
Excellent
that's a
idea.
very good idea. Yeah, right. So the mentors can also guide, and it can be more informal, the interaction for them, right? So, more questions? Any more questions? So actually, tomorrow when you hear the students talk, you'll see exactly what did they do with with these different samples which they were studying, and that would give you an idea of what kind of things could be done, right? So, are there any more questions? So the idea is that at present you hear the talks, and then people actually form their groups and work on particular projects, right? As per their thing.
Sushan's profile.
Yeah, you can. Oh yeah, Sushan, you were
Sushan, your
supposed to
profile.
tell us your profile and your little story.
Oh, okay. Yeah. Oh, yeah. I'm sorry. I totally forgot about that. Yeah. So my venture into astrophysics was a little not very straight. It was slightly sort of in a zigzag fashion. I was initially interested. I have always been interested in theoretical physics. And I wanted to understand physics of astrophysical objects. And I know I did not have a very clear idea what I wish to do. So I applied for the VSRP, the Visiting Summer Research Program at TIFR when I was doing my MSc. So I went there, I did a project, and I liked it. But my interest, I have always been very much interested in condensed matter. So condensed matter statistical mechanics. So I joined PhD in statistical mechanics condensed matter. And then at one point I felt that that project, interestingly, the statistical mechanics project that my supervisor gave me to work on was inflationary, basically associated with inflationary cosmology. So there are phase transitions there, and you can look at this from a phase transition point of view, the statistical mechanics point of view. And so that's what I started working on. Then at one point I realized that I really want to get into real astrophysics. So I got into, I moved, I was at IITK, I moved to ISC Bangalore, and I joined the Joint Astronomy program there. And there, once again, this love for condensed matter always stayed with me. And Neutron Star is, as I keep saying, that it's the most complex condensed matter system that that there is. Okay, so it's a love for trying to understand a difficult system, theoretical understanding of physics. And that's how I sort of slowly moved into astrophysics. My motivation to do astrophysics has basically been driven by my desire to understand a very complicated system. In astrophysics, what happens is, this is very different from other branches of physics in some sense, is that for example, if you talk about condensed matter, so you have a system, you want to understand that, and you take a sample to the lab, and you have a strong magnetic field, you have an electric field, you have this temperature, you have that humidity, whatever, you set up various conditions under which you test that sample, and then you try to build a theory, and so on and so forth. For astrophysical systems, what happens is you cannot do any such thing. There is that object up there in the sky, whatever signal is coming. Some weak signal you obtain, and even that you cannot sort of say that I want to test this object under such and such conditions. That's not there. You cannot do that. So you get some information and you have to um, uh, sort of interpret that. This requires a very good understanding of almost all of physics. It's not that, a condensed matter theorist, for example, can be a condensed matter theorist, a condensed matter expert, a high energy expert can be a high energy physics expert. An astrophysicist have to be expert in everything. An astrophysicist must know plasma physics, must know condensed matter physics, must know high energy physics. He or she should know everything. So that is a far bigger challenge. These systems are a far bigger challenge, and that is probably one of my motivations for moving into astrophysics and trying to look at various aspects of neutron stars that I work on. And so different people would have different motivations. What is important is give your best to it and work for what your personal aim is. You want to understand this particular system, so do whatever you want to do for that. You want to understand something, you want to test a hypothesis, you want to detect something, you want to find a pattern in a given set of observations. So whatever you do, you have to be consistent, you have to be persistent, and you have to learn all that is needed to learn, whether it is physics, whether it is mathematical techniques, whether it is computational packages. You have to slog and work on that. So that's what it is.
Yeah. And then another one, which is, I don't know whether it's often asked, but I need to ask it for completeness. What about a woman in astrophysics? What do you have to say about that?
Okay.
Because lots of girls here.
Okay, so yeah, I should, because let me tell them that ASI, our Astronomical Society of India, now has a working group for gender equity, and I was a person who worked for setting up that committee, me and many other people. So yeah, so what I want to tell young people here is that personally, when I was a student, when I did my research, when I did my PhD, I did not find gender discrimination. I did not. Does that mean that gender discrimination, I would not say gender discrimination, I would say gender inequality that exists. And my personal experience is that you would, the people who would harass you because you are a woman, that number, even though exists, is not very large. If you are competent enough, you are good enough, whether you are in a class or you are doing your research, if you are really, really competent, discrimination that doesn't really enter into the equation much. What will kill you, later point, is that our society doesn't have enough, what should I say, infrastructure for women to have a family, to take care of the children and do her own work. First of all, there will be, the problem of if you have a family, to have academic jobs are difficult to come by, and you do not have much choices. So if your partner, your spouse gets a job somewhere else and you get a job in another place, then that becomes very difficult. It becomes very difficult to have proper childcare because you do not have appropriate infrastructure everywhere. So that becomes very difficult. So these are the issues that become very difficult. But per se, gender discrimination, that's a factor, but not very important, not the important factor. And I would say that I have been very lucky. All my teachers, the entire environment was what I would say was gender neutral, in the sense that they saw me as a person. They did not see me as a woman. I'm very thankful for that. You are muted. You are muted.
Again, yeah. I said I would also agree with Sushan in number one that even I was lucky enough that I never ever faced any gender discrimination, never. And I do not think it is, obviously there are people who are affected, but it did not affect me. I was lucky enough or whatever. Agreed. I also agree with Sushan that the hurdle is obviously family and children and stuff like that. But it's not an impossible task to achieve.
No,
Right?
no, absolutely.
I have kids.
Absolutely
Sushan
not.
has kids, and there's absolutely no issue.
Yeah,
So
and
it's all doable.
yeah, so it's not really astrophysics, any kind of academic job, because
Yeah.
the time at which you must take up a job, or the possibilities of academic jobs, they are very constrained. So therefore, any career in academics, you really have to think how you would manage all that.
That's right. Yeah, so it involves a lot of some adjustments, some compromises, some ups and downs. That's there for sure. Yeah.
Yeah, it's very heartening to hear you say that. Very positive thing, because a lot of women, they do have issues and problems, and when you see the top positions in all institutes, and we see that there are not many women. Only recently we have a ASI director and even IIA director, but though women do very well in sciences at all stages, but you don't see too many on the top positions, and it is changing. It's not men against women. It's not that men want to put them down. It's not true. And you have to, like you said, you have to construct. Should have a system, an environment you have to create where you can function without getting bogged down and so on. So the hurdles are there for both men and women, more so for women because of our social.
Yeah, those are social issues.
Those are social issues.
Not to do with the subject. It is the
Absolutely, no, not to do with the subject.
expectation society has of a woman.
Yeah, and I also feel that what Najam is saying, that we do not have too many women on the top position. I think we have a backlog. And when I joined IIT Kharagpur, I was probably the second woman in that department. But now things have completely changed. So we are slowly getting there. I think things are changing, and soon become.
Very important thing which the ladies in the group have to realize is they don't have to give up on a family life to be an astrophysicist.
Absolutely,
Very balance both the things and go on.
Yeah, sometimes it gets conveyed that you have to sacrifice for the love of science type of thing, but I don't agree with that at all.
You have to be with the right person who can appreciate your interests and go on with it.
I was giving a talk. It was not a science talk to my school, where it's a girls' school, and I kept telling them that when you plan your career, it's not enough to plan just the career. You also have to plan your life. You have to think about what kind of person you want to spend your life with, because that would affect your career. So that must be folded into.
Yeah, great. Do we have any questions from the others? We have a unique opportunity to be discussing these kind of issues. Is there any participant also who would like to interact or ask ma'am something? Please do ask, because you don't get such opportunities very often. Is there anyone? So actually, Ayushi writes that she was about to ask the same question, so she's happy. But is there anybody else who wants to ask? You're most welcome. Okay. So I think everyone's fine. Anyone? Yeah. Yeah, I think the issue is basically of a career for a woman, and it's not specifically the astro bit. A little bit because of observations and stuff like that, you need to go to remote places, but
So
otherwise,
so again, it's a societal issue. So yeah, I actually I have heard about a student who started her PhD and was doing very well, but when the time came for her to go to observatories and take observations, her family had objections.
yeah.
These are societal problems that one needs to deal with.
Oh, there's another question, frankly asking, what's the future of students after having PhD in astrophysics related topics?
Okay, that's a difficult question. Difficult because the answer is not
Sushan, can you see it?
and I can't see that.
Okay, I'll repeat it again. What is the future of students after having PhD in astrophysics related topics? It's the chat.
Yeah. So the answer is not simple. There is no one answer to this because positions in academia are limited. So it's not that everybody would go into academia, and it's not even important, and it's not necessary. Not that everybody would, just because a person has done PhD doesn't mean that he or she wants to spend his or her life doing this kind of work. So one of the major avenues that are opening up because of the nature of astrophysical research is various organizations where big data handling is needed, because in astrophysics we learn how to sort of handle big data, various computational methods and so on. And so industrial sectors are opening up for in particular for astrophysics trained people. Of course, there are teaching professions, and there are at this point of time in India, newer and newer academic institutions are coming up, all of which may not be research institutes, but there are a whole bunch of teaching institutes coming up. So in universities and stuff like that. So those would be, I'm just assuming that the question is about other options other than academia. So people who would go into academia, they would go into academia and continue doing sort of continue along similar lines to their PhD period, but there are many other avenues that people can take up these days.
There's a related question. What challenges are to be faced in making a career in astronomy with science rather than, say, Btec or something else?
I am assuming the question basically means if you go into astronomy research and you are coming from Btec stream, not from physics MSc.
No, I think the question is, how would you compare a career, making a career in astronomy with sciences, basic sciences, rather than a career with Btec? I think that's the question. Saket, is that what you mean?
Yeah, yes, ma'am. Yeah.
No, I don't
career
understand.
choice. As a career choice, would a Btec, based career compared to a career in basic sciences?
What would be a Btec based career? I probably did not understand the question.
Probably means industry or what? I don't know. Sanket, can you unmute
yourself? Yeah. As a graduating from doing engineering or something like that, and as a graduating from taking a degree in physics as a bachelor's, and then doing career in astronomy.
Okay. No. There are opportunities. See, please understand that the two things here, that many engineers have gone on to become physicists of different kinds, condensed matter physicist, astrophysicist. So that is not an issue at all. In particular, in astronomy, there are all kinds of work that engineers can do much better than physicists can do. So, for example, there are specific observational techniques instrumentation techniques, which are done better by engineers than a person who has done a physics MSc. So if you are doing a Btec at this point of time and then want to do astronomy later on, there shouldn't be any problem at all.
Is he trying to ask whether it's safer or easier to get placed, get jobs as a Btech or settle down as an astrophysicist? Is that what you're asking?
No, sir. I got my.
Remember, if you go into research, if you go into any sciences, you have to spend for about 5 years of PhD. After your BSc, MSc, 5 years, and then a few postdocs. And only when you are in your 30s, you start getting chances of getting positions, if you are lucky, in institutes or in universities. While in a BTech, right after you are, at the age of 22, 23, you can get a job because you are directly into an applied science and you get placed very well. And further, astronomy is a specific, specialization. So there are not many universities which offer astronomy as a subject. So it's safer that way or easier to get a job as a physicist or a mathematician because mathematics is taught at all levels. BTechs learn it, you have it at masters, you have it at all degrees, while astronomy could be very specific only in certain places, right? But then you have to do something which you love doing, which you enjoy doing. And like Professor Sushan said that you develop certain skills while doing astronomy, which can be applied anywhere else. You needn't be in academia. There are people who have moved into industry, they've gone into banking, who had done astrophysics at a very serious level. Yeah, because they could handle data, they could understand of it, and those are the skills. Those are the skills you need to learn and build your career with that. Yeah, so yeah, it's a tough job getting into sciences, but it's worth it. It's fun. We don't regret it.
So there's a related question. There's Ayushi, who's actually interested both in instrumentation as well as astrophysics. So what would you suggest? Is it better for her to do an MTech and join an institute later, or take the pure physics route if she wants to do instrumentation and astrophysics?
There are places where both astrophysics instrumentation is done. I mean, instrumentation for the purpose of astrophysics. That is done. In particular, even at IUCA.
That's right.
Labs exist where.
Or now I also, University of Astrophysics has a
absolutely
specifically for BTechs, and it's it's basically oriented towards instrumentation. So it would be like an MTech PhD types. So actually now things have opened in the way that you can do it through both ways. And it's very difficult to say which would be better because it depends on you and the kind of instrumentation you're trying to do. So this thing. And Tejinder asks, ma'am, is there any scope of MSc Physics and PhD along with a job? You mean to say, so part-time MScs, and there are many correspondence courses with which you can do an MSc, right? There are many places where you can do correspondence or distance MSc. But PhD, I don't know of a distance PhD. For that, you can be a part-time PhD scholar in some place. So with your job, you can do the PhD, no problem. So do your
PhD, a lot of people do that.
Yeah, you can do part-time PhD. We have it even in our university. So the student registers as a part-time PhD and you get more time. So a full-time PhD gets 4 years, a part-time PhD gets 5 years. So you can do that. You can.
That you need to take leave
in
between.
So obviously there are nuances in the sense, officially your place of work has to give you permission to join and stuff like that. But in principle, it's doable. You can do it. Do your MSc correspondence and join part-time PhD. That's doable. Yeah.
We had a PhD student at IIT Kharagpur. He was doing his PhD when he had a school teaching job, and he was doing his PhD. So he finished his PhD and did a postdoc and joined the Premier Institute later.
Oh, that's so good. That's so nice.
Thank you, ma'am.
Okay, thanks.
And Professor, probably you knew of Professor Aladdin.
Sushan.
Yeah, no, I don't know about him.
He was well known in galaxy
No,
dynamics.
I know about him, but I don't know the story that.
One of his students who he was teaching in college, and he joined him, and the student was older than the supervisor. But then the first paper they published came as a review in a very lead journal. So he did extremely well. He joined at a very late age.
So yeah, this person actually joined for PhD after retirement. When he retired with a younger supervisor, but that's fine. You know him. He's Professor Narasimham. He used to take the galaxy dynamics courses in Ayuka for grad school. Sharon asks, how can I use my Btec level knowledge to jump in the field of astrophysics? I studied electronics instrumentation in undergrad. So is it good to do an MSc physics course now, or there are other master's courses specifically where I can use my bachelor's degree?
BTECs usually, I mean, if they can cross the interview, they join PhD.
Yeah, there's no problem. Yeah. So but basically you need to clear the entrance exams, the JEST or GATE or something like that, and you can definitely get into this thing. No problem.
NCR is a good place where she can try.
And NCR is specifically where Sushan is, since they have the radio telescope. I think there's even more scope for engineering background people, right, with NCR.
Electrical and electronics.
Yeah. Yeah.
Not here. MTech in astronomical instrumentation, at least there is nothing like that in India.
But what I has started in Institute of Astrophysics, the integrated PhD program in which they take in physics.
So that's that's a combined thing.
So have a look at the page of Indian Institute of Astrophysics and check on that. Yeah. Okay. So I'm sorry we've kept you for very long.
No. This is very enjoyable. Talking to the students is always enjoyable.
Yeah. I don't see any more questions. Is there anything else? Okay. For part-time MSc, all these universities, I think IGNOU also has it, but there are lots of universities with distance mode for MSc, Rajinder. I think the Hyderabad Ambedkar University has. You'll have to check. I'm not too sure.
Yeah, and then the new education policy, the way we are moving now, they are going to have no distinction between a distance mode degree and a regular one. So what the UGC is trying to push through is it would not be mentioned on the degree whether you are a part-time, you are a distance mode one or this one. So it's going to get even more easier soon. IGNOU should have MSc Physics.
Yeah.
Just check up.
So check for IGNOU.
MSc Mathematics is there in many places because you don't require a laboratory. But with science, physics and all, it could be a bit tricky. It's not there everywhere. But there are some places which offer it. And you can do an MSc Mathematics and then get into astronomy, astrophysics, dynamical astronomy.
Okay, he's already MSc Maths. Then you can join for a PhD program where even in astro, if you're from a related background, maths, physics background, you can join for a PhD program. So you can in principle.
IGNOU has IGNOU.
Okay, IGNOU has PhD physics also. Very good. Oh, Mudassir says that. So check IGNOU. And IGNOU course material and all is very nice. It's very well written.
IGNOU does not have this.
Okay. So IGNOU does not have distance MSc, but you can have a look. You can check. I'm sure there are places where you can do it. Yeah.
Okay.
Yeah.
So thanks a lot.
So thanks, Sushan. Thanks so much.
Most welcome. Actually, thanks to you. You are organizing this wonderful thing.
No, but I thought that it does have some sense to have a little bit of informal interaction, because many of these students have questions which they really don't know, which are important for them to plan.
Right.
Yeah. So thanks so much, and see you tomorrow. We'll meet again tomorrow.
Yeah, sure.
See you. Bye bye, everyone. Bye.
Bye. Bye.